As you rest peacefully tonight beneath the darkness, look up through your window toward the stars and notice something remarkable. They twinkle, they shimmer and dance, changing brightness and sometimes even color from moment to moment, creating the gentle sparkling that has inspired poets and romantics throughout human history. But this twinkling is not a property of the stars themselves, burning steadily, millions or billions of miles away. Instead, it's a beautiful illusion created by Earth's atmosphere, a visual effect that reveals the invisible turbulence in the ocean of air above you. Tonight, as you drift towards sleep, you'll discover why stars twinkle while planets shine with steady light, how Earth's atmosphere bends and distorts the light from distant suns, what astronomers do to see past this atmospheric interference, and why the twinkling you see reveals information about both the stars above and the air through which their light travels to reach your eyes. The technical term for twinkling is scintillation, the rapid variation in brightness and position of a celestial object caused by its light passing through Earth's turbulent atmosphere. This atmosphere, the protective blanket of gases surrounding our planet, extends roughly 60 miles above the surface, though most of the atmospheric mass concentrates in the lowest 10 miles. Light from stars must travel through this entire atmospheric column before reaching your eyes. And during that journey, it encounters layers of air with varying temperatures, pressures, and densities. When light travels from one medium to another, from space into air, or from one air layer to another of different density, it bends in a phenomenon called refraction. You've seen this effect when a straw appears bent in a glass of water, or when heat waves rise from hot pavement and distort the view beyond. The same principle operates on a grander scale in Earth's atmosphere, where constantly shifting air currents create momentary lenses that bend starlight in ever-changing ways. Imagine starlight as a narrow beam traveling through 60 miles of air that is never perfectly still. The atmosphere is constantly in motion. Wind currents flow at different speeds and directions at various altitudes. Warm air rises while cool air sinks. Jet streams race across the upper atmosphere at hundreds of miles per hour. And countless small-scale turbulence patterns swirl and mix air masses of different temperatures. All this motion creates temporary variations in air density, and each density variation slightly changes how much the air bends passing light. As starlight passes through these turbulent air layers, it's refracted, bent by tiny amounts in constantly changing directions. Sometimes multiple paths of light from the same star are refracted differently, causing the star to appear momentarily brighter when the paths converge toward your eye, or dimmer when they diverge. This rapid fluctuation in brightness, combined with tiny apparent changes in position, creates the twinkling effect you observe. The dancing quality of starlight intensifies near the horizon, where light must travel through more atmosphere to reach you. When you look straight up, starlight travels through roughly 60 miles of atmosphere. When you look toward the horizon, the same light must pass through several hundred miles of atmosphere at an oblique angle, encountering more turbulent air and experiencing more refraction. This is why stars near the horizon twinkle more vigorously and may even appear to flash different colors as different wavelengths are refracted by varying amounts. The color changes in twinkling stars occur because different wavelengths of light refract by slightly different amounts, a phenomenon called dispersion. the same physics that creates rainbows when white light passes through water droplets. When atmospheric turbulence momentarily acts as a prism, it can separate a star's white light into component colors, causing the star to flash red, then blue, then white in rapid succession, especially when viewed near the horizon, where the effect is strongest. Weather conditions dramatically affect how much stars twinkle. On nights with stable, calm air, often during high-pressure systems with light winds, stars twinkle less because the atmosphere is relatively still and uniform. On turbulent nights with strong winds aloft, approaching storm systems, or significant temperature differences between air layers, stars twinkle more energetically because atmospheric disturbances are more pronounced. Experienced observers can judge atmospheric stability by watching how vigorously stars twinkle. As you prepare to explore the science of stellar scintillation tonight, rest in the knowledge that the twinkling stars above you are revealing information about the invisible atmosphere through which you're looking. Every shimmer represents atmospheric motion. Every color change demonstrates light's interaction with moving air. And every moment of watching stars twinkle connects you to both the distant cosmos and the dynamic atmosphere that protects and sustains life on Earth, while creating this beautiful optical phenomenon. The path through air, how atmosphere bends starlight. Journey now into Earth's atmosphere, following starlight on its path from space to your eyes, discovering how layers of air with different properties act like constantly shifting lenses that bend, distort, and split the narrow beams of light from distant stars, creating the scintillation that makes stars appear to dance. Earth's atmosphere is not uniform, but stratified into layers with distinct characteristics. The troposphere, extending from the surface to about 6 to 10 miles altitude, contains most atmospheric mass and all weather phenomena. Above it lies the stratosphere, reaching about 31 miles, then the mesosphere to about 53 miles, and finally the thermosphere, extending to several hundred miles. Each layer has different temperature gradients, pressures, and wind patterns that affect how light passes through. Within these layers, temperature variations create differences in air density. Warm air is less dense than cool air because heat causes gas molecules to move faster and spread farther apart. When a horizontal beam of starlight encounters a boundary between warm and cool air, it bends towards the denser, cooler region, much as light bends when entering water from air. These temperature boundaries constantly shift as air masses move, creating ever-changing refraction patterns. The jet streams, narrow bands of fast-moving air in the upper troposphere and lower stratosphere, create particularly strong optical disturbances. These atmospheric rivers flow at speeds sometimes exceeding 200 miles per hour, carrying air masses of different temperatures and creating sharp boundaries where significant refraction occurs. Starlight passing through or near jet stream locations experiences particularly vigorous scintillation. Smaller-scale turbulence creates the rapid fluctuations that characterize stellar twinkling. Atmospheric turbulence exists at all scales, from enormous weather systems thousands of miles across to tiny eddies just inches in size. For astronomical observations, turbulence cells ranging from inches to several feet in size are most important, because they're comparable to the aperture of the human eye, or small telescopes, meaning individual turbulent cells can affect the entire light path into your eye at once. The Kolmogorov theory of turbulence, developed by Soviet mathematician Andrei Kolmogorov, describes how turbulent energy cascades from large-scale flows to progressively smaller eddies until it dissipates as heat through molecular viscosity. This theory helps astronomers understand and model atmospheric turbulence, predicting how it will affect observations and informing the design of adaptive optics systems that compensate for atmospheric distortion. Wind shear, the change in wind speed or direction with altitude, creates particularly troublesome optical disturbances. When adjacent air layers move at different speeds or in different directions, they create turbulent boundaries that significantly distort passing light. Strong wind shear produces more vigorous stellar scintillation, while calm, uniform winds create more stable viewing conditions. The seeing conditions, as astronomers call the steadiness of the atmosphere for optical observations, vary dramatically with location, season, and time of night. Some of the world's premier astronomical observatories are located in places with exceptionally good seeing. High-altitude sites like Mauna Kea in Hawaii, the Chilean Andes, and the Canary Islands, where atmospheric turbulence is minimal, allowing clearer views of the cosmos, despite the unavoidable presence of Earth's atmosphere. Differential refraction, the varying amount of bending experienced by different wavelengths of light, creates the color changes sometimes visible in strongly twinkling stars. Blue light refracts slightly more than red light when passing through atmospheric density gradients, causing the star's light to be briefly separated into component colors. This effect is most noticeable for stars near the horizon, where light passes through more atmosphere and atmospheric dispersion is strongest. The refractive index of air, its light-bending power, depends on temperature, pressure, and humidity. Dry air refracts more than humid air at the same temperature and pressure, while cold air refracts more than warm air. As these conditions vary throughout the atmosphere and change over time, the effective lens created by the atmosphere constantly shifts, creating the variable bending that manifests as stellar scintillation. Atmospheric coherence length, also called the Freed parameter, after astronomer David Freed, quantifies the size of atmospheric turbulence cells. On a night with good seeing, the coherence length might be 4 to 6 inches, meaning turbulent cells are relatively large and create less rapid scintillation. On nights with poor seeing, coherence length shrinks to perhaps 1 to 2 inches, creating more numerous, small turbulent cells that produce more vigorous twinkling. The time scale of stellar scintillation, how quickly stars change brightness, relates to wind speed in the upper atmosphere. Faster winds move turbulent air cells across your line of sight more rapidly, creating quicker brightness fluctuations. On calm nights, scintillation occurs more slowly. By timing how rapidly stars twinkle, astronomers can estimate wind speeds in the upper troposphere without directly measuring them. As you rest peacefully tonight, imagine starlight traveling from distant suns through 60 miles of ever-moving atmosphere, being bent by warm air here and cool air there, refracted one way then another as turbulent eddies spin and shift, arriving at your eye with brightness and position that fluctuate many times per second, creating the gentle twinkling that transforms steady stellar light into the shimmering points that make the night sky feel alive and dynamic. Points and disks. Why planets don't twinkle like stars. Discover now the crucial difference between stars and planets that explains why stars twinkle vigorously while planets shine with steady, unwavering light. a difference that reveals fundamental principles of optics and allows you to distinguish between these two types of celestial objects simply by watching how their light behaves. Stars are so incredibly distant that even through the largest telescopes, they appear as perfect points of light with no measurable diameter. The nearest star beyond our Sun, Proxima Centauri, lies 4.2 light-years away, about 25 trillion miles. At this enormous distance, even though Proxima Centauri is actually much larger than Earth, it appears as an infinitesimally small point from our perspective. This point-like appearance is crucial to why stars twinkle. When light from a point source travels through turbulent atmosphere, the entire beam experiences the same refraction at any given moment. If atmospheric turbulence bends the light path slightly to the left, all the light from that star shifts left together. If turbulence makes the path converge toward your eye, the star appears momentarily brighter. Because all the light comes from a single point, atmospheric effects affect the entire image simultaneously, creating noticeable brightness variations and position shifts, the twinkling you observe. Planets, in contrast, are much closer to Earth and appear as tiny disks rather than points, even though these disks are too small to resolve with the naked eye. Jupiter, at its closest approach to Earth, is only about 400 million miles away, roughly 60,000 times closer than Proxima Centauri. At this distance, Jupiter's actual diameter of about 87,000 miles subtends a measurable angle of about 50 arcseconds, about 1/70,000th of a degree, making it appear as a small disk rather than a perfect point. This disk appearance, even though too small for your eye to resolve into an actual visible disk, makes all the difference for twinkling. A planet's light reaches your eye from many slightly different directions simultaneously. From the left edge of the disk, the right edge, the top, bottom, and center. Each of these light paths passes through slightly different atmospheric turbulence cells, experiencing different refraction at any given moment. When atmospheric turbulence brightens light from one part of the planet's disk, other parts may be dimmed by different turbulence cells elsewhere in the atmosphere. These brightness changes average out across the planet's apparent disk, creating much more stable overall brightness than you'd see from a point source. Similarly, while turbulence may shift light from one edge of the disk slightly left, it might shift light from the other edge slightly right. And these position variations also average out, making the planet's overall position appear stable. The mathematical principle underlying this effect is called spatial averaging. Because planets subtend a measurable angle and their light arrives from multiple directions, the random brightness and position fluctuations caused by atmospheric turbulence partially cancel out through statistical averaging. The larger a planet's apparent disk, the more effective this averaging becomes, and the less the planet twinkles. You can use this difference to distinguish planets from stars with the naked eye. If you see a bright point of light in the sky and aren't sure whether it's a star or planet, watch it carefully for a few minutes. If it twinkles noticeably, it's almost certainly a star. If it shines with steady, unwavering light, it's likely a planet. This simple observation technique allowed ancient astronomers to identify planets, wandering stars, that moved against the background of fixed stars, long before telescopes revealed their disk-like appearances. Venus, being both large and relatively close to Earth, shows the least twinkling of any planet. At its largest apparent size, Venus can subtend over 60 arcseconds, making its disk large enough for spatial averaging to nearly eliminate twinkling under all but the most turbulent atmospheric conditions. Jupiter, slightly smaller in apparent size, also shows minimal twinkling. Mars, smaller and more distant, twinkles slightly more than Venus or Jupiter, but still far less than any star. Mercury, the smallest and most distant of the naked eye planets, occasionally shows slight twinkling when near the horizon, where it must shine through maximum atmospheric thickness. Its small apparent size, typically less than 10 arcseconds, provides less spatial averaging than larger planets, allowing some atmospheric effects to create noticeable scintillation, though still less than stars experience. Interestingly, planets do twinkle slightly when observed through powerful telescopes. The telescope magnifies the planet's disk, revealing details like cloud bands on Jupiter or the polar caps of Mars. But this magnification also makes atmospheric effects more apparent. Astronomers watching planets through telescopes see the image boil and shimmer as atmospheric turbulence distorts the view, though the overall brightness remains steadier than stellar observations because of continued spatial averaging across the planet's now visible disk. The Moon, Earth's largest apparent celestial disk aside from the Sun, never twinkles, because its huge apparent diameter, about half a degree, or 1,800 arcseconds, provides such effective spatial averaging that atmospheric effects are completely smoothed out. Even the Sun, despite being a stellar object, doesn't appear to twinkle during the day because its apparent disk, about 1,900 arcseconds, is too large for atmospheric effects to create noticeable brightness variations. As you drift towards sleep tonight, you can appreciate that the simple act of watching whether celestial objects twinkle or shine steadily reveals fundamental information about their distance and size. The twinkling stars are distant suns, so far away they appear as points, while the steady planets are nearby worlds close enough to show measurable disks that average out atmospheric distortions, creating the peaceful, unwavering light that makes planets easy to identify in the night sky. Seeing through the shimmer, how astronomers overcome twinkling. Contemplate now the remarkable technologies astronomers have developed to see past atmospheric twinkling. From choosing observatory locations with exceptional seeing, to building adaptive optics systems that correct for atmospheric distortion in real time, demonstrating human ingenuity in overcoming natural limitations to achieve clearer views of the cosmos. The simplest solution to atmospheric twinkling is to go above the atmosphere entirely. The Hubble Space Telescope, orbiting 340 miles above Earth's surface, operates in the vacuum of space where no atmosphere exists to distort its view. The images Hubble captures show stars as perfect, unshimmering points, revealing details impossible to see from ground-based observatories, no matter how large or sophisticated. This was one of the primary motivations for building space telescopes, to escape atmospheric interference entirely. The James Webb Space Telescope, positioned nearly 1 million miles from Earth at the second Lagrange point, similarly operates in space without atmospheric distortion. Its infrared observations can detect celestial objects and phenomena invisible to ground-based telescopes, not just because of its sensitivity, but also because it experiences no atmospheric scintillation or absorption of infrared wavelengths. For ground-based observations, selecting observatory sites with excellent natural seeing is crucial. Astronomers prefer high-altitude locations because less atmosphere lies above them, reducing the total atmospheric distortion light must traverse. Mountain peaks like Mauna Kea in Hawaii, 13,796 feet elevation, and Cerro Paranal in Chile, 8,645 feet, place telescopes above much of the turbulent lower atmosphere. Sites are also chosen for atmospheric stability. Locations with laminar, smooth, non-turbulent airflow, minimal jet stream activity, and stable temperature profiles produce less stellar scintillation. Islands in the middle of oceans often have excellent seeing because ocean temperature moderates air temperature variations, reducing thermal turbulence. Desert locations at high altitude, like Chile's Atacama Desert, combine high elevation with exceptionally dry, stable air. Site testing involves years of measurements before building major observatories. Astronomers deploy instruments that measure atmospheric seeing conditions, wind speeds, temperature gradients, humidity, and sky brightness. These data reveal which locations offer the best natural conditions for clear, steady views of the heavens, justifying the enormous expense of constructing observatories in remote, challenging locations. Even with excellent sites, atmospheric turbulence affects observations, leading to the development of adaptive optics, AO, sophisticated systems that measure atmospheric distortion and compensate for it in real time. A typical AO system includes a wavefront sensor that measures how atmospheric turbulence has distorted incoming light, a computer that calculates the corrections needed, and a deformable mirror that changes shape hundreds of times per second to counteract the distortion. The deformable mirror in an adaptive optics system contains actuators, small pistons or mechanisms, that can push and pull different parts of the mirror surface, creating a controlled distortion that is the inverse of atmospheric distortion. If turbulence creates a bump in the wavefront, the mirror creates a corresponding dip. When distorted light reflects off this precisely deformed mirror, the distortions cancel out, producing a corrected image nearly as sharp as if no atmosphere existed. Adaptive optics requires a bright reference star near the target object to measure atmospheric distortion. For targets without nearby bright stars, astronomers use laser guide stars, powerful lasers pointed at the sky that excite sodium atoms in the mesosphere about 56 miles up, creating an artificial star that serves as a reference for the wavefront sensor. This breakthrough allows AO correction for objects anywhere in the sky. The performance of adaptive optics is measured by the Strel ratio, the peak brightness of the corrected image compared to the theoretical maximum achievable with perfect optics and no atmosphere. A Strel ratio of 1.0 would indicate perfect correction. Modern AO systems achieve Strel ratios of 0.6 to 0.8 in the infrared, providing images 60 to 80% as sharp as space-based observations, but from ground-based telescopes that are cheaper to build and maintain. Long exposure photography helps average out some scintillation effects. When photographers or astronomers keep camera shutters open for minutes or hours, the random brightness fluctuations of stars average out over time, while the star's average position remains constant. This time averaging creates sharper images than instantaneous snapshots would achieve, though it doesn't completely eliminate atmospheric effects. Lucky imaging represents another technique for dealing with atmospheric turbulence. By taking thousands of very short exposures and selecting only those moments when atmospheric seeing happened to be exceptionally good, the lucky moments, astronomers can compile images nearly as sharp as adaptive optics provides. Computer algorithms automatically identify the sharpest frames and discard the rest, effectively filtering out atmospheric turbulence through selective sampling. Interferometry combines light from multiple telescopes separated by large distances, creating resolution equivalent to a single telescope with a diameter equal to the spacing between the individual telescopes. While atmospheric turbulence still affects each telescope individually, Sophisticated signal processing can partially compensate for these effects, allowing interferometers to achieve incredible resolution despite atmospheric interference. Amateur astronomers have also developed techniques to minimize twinkling's effects on their observations. Using short exposures and stacking many images allows averaging out scintillation. Observing during stable atmospheric conditions, often on winter nights with high-pressure systems, provides naturally better seeing. Even simply waiting for objects to reach higher altitudes in the sky, where light passes through less atmosphere, reduces twinkling and improves image quality. As you rest peacefully tonight, feel reassured that while Earth's atmosphere creates the beautiful twinkling you see when looking at stars, human ingenuity has developed numerous ways to see past this shimmer, allowing astronomers to study the cosmos with clarity that would have seemed impossible just decades ago, proving that understanding natural phenomena leads to technologies that overcome natural limitations, while maintaining wonder at both the challenge and its solution. Other worlds, other skies, how atmospheres affect views throughout the universe. Journey now beyond Earth to imagine how twinkling and atmospheric effects would appear from other worlds, discovering that every planet with an atmosphere creates its own unique scintillation patterns, while airless worlds offer perfectly steady starlight, revealing how atmospheric properties shape astronomical observations throughout the solar system and beyond. On the Moon, where no atmosphere exists, stars never twinkle. Astronauts standing on the lunar surface see stars as perfectly steady points of light that neither shimmer nor change brightness, even when viewed near the lunar horizon. This unwavering starlight creates a sky that feels profoundly different from Earth's, more static, less alive, but optically perfect for astronomical observations. The Moon's lack of atmosphere makes it an ideal location for future lunar observatories. Mars has a thin atmosphere, only about 1% the pressure of Earth's at the surface, composed primarily of carbon dioxide. Stars observed from Mars would twinkle slightly, but much less vigorously than from Earth because the thinner atmosphere creates less refractive distortion. Martian scintillation would be most noticeable for stars near the horizon, where light passes through the maximum atmospheric column. But overall, Mars provides much steadier astronomical viewing than Earth. Dust storms on Mars dramatically affect atmospheric seeing. During global dust storms that occasionally envelop the entire planet, suspended dust particles would scatter and absorb starlight, reducing visibility and potentially creating unusual scintillation patterns. Between storms, when Mars's atmosphere clears, the thin, stable air would provide excellent seeing conditions for hypothetical Martian astronomers. Venus, with its extremely dense atmosphere, 92 times Earth's surface pressure, would make stars twinkle violently if you could see them through the thick cloud layers. The massive atmospheric column and extreme density gradients created by Venus's runaway greenhouse effect would cause severe scintillation. However, the complete cloud cover makes stellar observations impossible from Venus's surface, demonstrating that too much atmosphere can be worse for astronomy than too little. Jupiter and Saturn, being gas giants, have no solid surfaces from which to observe, but their atmospheres would create extreme scintillation if viewed from within. The turbulent, rapidly rotating atmospheres with wind speeds exceeding 300 miles per hour would cause stars to twinkle ferociously. Any hypothetical observatory in these planets' atmospheres would need to be positioned high above the dense lower layers to achieve usable astronomical observations.
Titan, Saturn's largest moon, has a thick nitrogen atmosphere with surface pressure 1.5 times Earth's, making it the only moon in the solar system with a substantial atmosphere. Stars observed from Titan's surface would twinkle significantly, though perhaps differently than from Earth due to the atmosphere's different composition and temperature structure. The thick hydrocarbon haze might reduce stellar visibility, but clear periods would offer interesting scintillation patterns. Exoplanets orbiting distant stars might have atmospheres with compositions and structures completely unlike anything in our solar system. A planet with an atmosphere of hydrogen or helium would create different refractive effects than Earth's nitrogen-oxygen atmosphere. Planets with extreme temperature gradients or unusual atmospheric circulation patterns might produce scintillation patterns unlike anything we observe from Earth. On planets orbiting close to their stars, extreme atmospheric heating could create severe turbulence and temperature gradients that would cause intense stellar scintillation. Conversely, tidally locked planets with one side permanently facing their star might have more stable atmospheres on their dark sides, potentially offering good astronomical seeing despite proximity to their host star. Rogue planets, working its from their stellar systems and wandering through interstellar space, would experience no stellar scintillation from a host star, simply because they have no nearby star to observe. However, the distant stars visible from rogue planets would twinkle based on the planet's atmospheric properties, creating night skies where all visible stars twinkle equally, since all are at similarly enormous distances. Space stations and habitats in the vacuum of space would enjoy perfectly steady starlight from all directions. Future space-based civilizations would grow up seeing stars that never twinkle, potentially finding Earth's twinkling stars strange and unusual during visits to planetary surfaces. The psychology of growing up under steady stars versus twinkling stars might subtly influence cultural perspectives on the heavens. Binary planet systems, where two large worlds orbit each other, might create interesting atmospheric effects. If both planets have atmospheres, observers on each world would see the companion planet shine steadily due to its large apparent disk providing spatial averaging, while stars twinkle normally. This contrast would make the relationship between the two worlds feel more immediate and tangible than stellar distances. On planets with multiple moons creating frequent eclipses, twinkling stars might occasionally appear to stabilize when a moon's shadow blocks solar heating of the atmosphere, temporarily reducing convective turbulence. This correlation between eclipses and improved seeing could have cultural significance for civilizations developing astronomy on such worlds. Future human settlements throughout the solar system will experience dramatically different night skies based on local atmospheric conditions. Martian colonists might appreciate slightly twinkling stars as a familiar touch of home, while lunar settlers would need to adjust to the unchanging stellar points. These varying experiences would create diverse cultural relationships with the night sky across different worlds. As you drift towards sleep tonight, appreciate that Earth's atmosphere creates a unique view of the cosmos, neither perfectly clear like airless worlds, nor completely obscured like Venus. The twinkling stars you see represent a balance between atmospheric protection that makes life possible and optical distortion that challenges
but doesn't prevent astronomical observation, creating the dynamic, living night sky that has inspired humanity throughout our existence.
The romance of twinkling. What shimmering stars mean to us. Rest now in contemplation of what twinkling stars have meant to human culture. How this optical phenomenon has inspired poetry and music, shaped our emotional relationship with the night sky, and continues to create a sense of wonder that connects us to the cosmos, even as we understand the physics behind the shimmer. The most famous celebration of stellar twinkling is surely Twinkle, Twinkle, Little Star, the children's song adapted from a 19th century poem by Jane Taylor. This simple verse captures the wonder children feel when first noticing that stars appear to shimmer and dance, expressing curiosity about what stars are and marvel at their mysterious nature. Generations of children have learned to look up at the night sky through this song, their first lesson in observational astronomy. Poets throughout history have used twinkling stars as metaphors for hope, guidance, impermanence, and beauty. The shimmer of starlight evokes feelings of magic and mystery, of looking across vast distances at lights that seem to flicker with their own life. Understanding that twinkling results from atmospheric turbulence doesn't diminish this emotional impact. If anything, knowing the scientific cause adds layers of meaning about Earth's protective atmosphere and the challenge of seeing clearly across cosmic distances. The distinction between twinkling stars and steady planets provided ancient astronomers with their first way to identify planets. The word planet comes from the Greek planetes, meaning wanderer, because these objects moved against the background of fixed stars. Their steady light was an additional identifying characteristic that made them seem fundamentally different from stars, contributing to ancient cosmological models that placed planets in a different category from fixed stars. For sailors navigating by stars throughout history, the steadiness or twinkling of celestial objects provided practical information. Planets, shining steadily, were easier to use for navigation than twinkling stars. The planet Venus, when visible, was particularly valued as a navigation reference because its bright, unwavering light could be seen even in twilight and remained constant throughout the night, providing a reliable directional reference. Twinkling intensity varies with altitude, providing experienced observers with intuitive information about atmospheric conditions. When stars near the zenith, straight overhead, twinkle noticeably, it indicates turbulent air, even in the upper atmosphere, often preceding weather changes. When only horizon stars twinkle, while overhead stars remain steady, it suggests stable conditions aloft, with turbulence confined to lower atmospheric layers. The color changes in strongly twinkling stars, flashing red, blue, and white, have inspired descriptions of stars as jewels or fires flickering with multiple colors. Sirius, the brightest star in the night sky, appears to flash with particularly vivid colors when viewed near the horizon, earning it descriptions as a diamond, a flickering flame, or a celestial lighthouse in various cultural traditions. Light pollution in modern urban environments has made star twinkling less observable for many people, who see only a few of the brightest stars through the glow of artificial lighting. This diminishment of the twinkling night sky represents a loss of connection to natural phenomena that shaped human culture for millennia. Dark sky preserves and rural observing sites allow people to reconnect with the full experience of a sky filled with twinkling stars.
Amateur astronomers often develop affection for the imperfections created by atmospheric twinkling, appreciating the challenge of capturing clear images despite atmospheric interference, and celebrating moments when seeing conditions are exceptional. The variable nature of atmospheric seeing makes excellent viewing conditions feel special and earned rather than guaranteed, adding to the satisfaction of successful observations. The twinkling of stars serves as a reminder that we observe the universe through a filter, the atmosphere that protects us, but also limits our vision. This teaches humility about human knowledge and encourages the development of tools and techniques to overcome natural limitations. The progression from naked eye observations limited by twinkling to space telescopes that eliminate it entirely represents human technological advancement driven by curiosity about the cosmos.
Children often first develop interest in astronomy by noticing that stars twinkle, asking questions about why this happens, and learning that simple observations can lead to understanding physical principles. This educational pathway from observation to explanation to deeper investigation exemplifies how natural phenomena inspires scientific curiosity and learning, making atmospheric scintillation not just an optical effect, but a gateway to scientific understanding. The ephemeral, constantly changing nature of twinkling reminds us that our view of the universe is dynamic, affected by conditions in our own atmosphere. This connects astronomical observation to meteorology and atmospheric science, demonstrating that understanding the cosmos requires understanding our own planet first. The study of stellar scintillation has contributed to knowledge of atmospheric turbulence that applies to weather forecasting, aviation, and climate science. As you drift into peaceful sleep tonight, rest in the knowledge that while twinkling stars represent atmospheric distortion that challenges astronomers, this same phenomenon creates the living, dynamic quality that makes stargazing emotionally engaging for casual observers. The shimmer of starlight connects you to Earth's protective atmosphere, to the physics of light refraction, to ancient navigators who used steady planets for guidance, to children learning to wonder about the sky, and to the eternal human desire to see clearly across vast distances, to the cosmic realm where stars burn with steady light. Even though their light reaches us dancing and twinkling through the turbulent ocean of air that makes life on Earth possible. Sleep well beneath the shimmering stars, where atmospheric turbulence creates beauty from optical interference, where steady planets reveal themselves by their unwavering light, where human understanding transforms childhood wonder about twinkling lights into sophisticated knowledge of atmospheric physics, all while maintaining the fundamental sense of awe that comes from looking up at the night sky and seeing the cosmos dancing through Earth's living, moving atmosphere. Sweet dreams under the stars, where twinkling reveals both the atmosphere that protects you and the distant suns whose light travels for years across space, only to be gently scrambled by the last few dozen miles through Earth's air, creating the shimmer that makes the night sky feel alive, dynamic, and eternally worthy of wonder. As consciousness fades into sleep, stars continue their steady burning, trillions of miles away, their unwavering light traveling through the vacuum of space, before passing through Earth's turbulent atmosphere, where moving air bends and distorts the photons in ever-changing patterns, creating the twinkling that transforms the night sky from a static photograph into a living display that breathes with atmospheric motion, reminding you with every shimmer that you observe the cosmos through the protective veil of air
that makes observing anything possible at all.